What's up, everyone? Welcome back. Patrick here. Moving on to another word problem dealing with quadratic relations. This is a pretty cool one. So we're told that the sum of the first n natural numbers are just basically all the positive integers. So starting at 1, 2, 3, 4, 5, etc., etc. We're told that the sum of the first n natural numbers is a quadratic relation. And so given that information, we have to, in part A, first confirm it's a quadratic relation. In part B, we have to find the actual quadratic relation. And then in part C, we have to find the sum of the first 50 natural numbers. So obviously with part C, what we're going to do is we're going to use the quadratic relation that we find, the equation that we find in part B, because taking the first 50 natural numbers, summing them all up, like 1 plus 2 plus 3 plus 4, etc., all the way to 50, would take us quite a while. So to start this question off, let's actually create a table of values comparing the first n natural numbers and then the sum of them. So what I'm going to do is I'm actually going to introduce two variables. I'm going to let, we already have n listed here, so we're going to let n equal the number of the first natural numbers. Okay, I'm going to explain more in detail what that means in a second. And then what I'm going to do is I'm going to let S equal the sum of that list right there. So the sum of the first n natural numbers. And so what we can do is we can create a table of values for this relation. So we could let this be n, we could let this be s. So s, notice that the sum, it's dependent on which number of the first natural numbers we are using, right? And if you wanted to still use x and y, this would be like x, this would be y, right? But I'm going to use something a little bit more appropriate for the wording that we are using in this question. So I'm going to use n and s, especially because we are told we're dealing with the first n natural numbers. So I'm just going to use that variable. So here's how it works. Let's say that n is 1. Okay, what is, if n is 1, that's the first natural number, which is just 1. Well, what's the sum of this? It's just 1. It's just that number by itself. Okay, now what if n is equal to 2? What would be s? Well, we would list out the first two natural numbers, so it would be 1 plus 2, right? The sum of the first two natural numbers would be 3. So s would be 3 for an n value of 2. Okay, and then what if n is 3? Well, we would have 1 plus 2 plus 3, right? The sum of the first 3 natural numbers, 1 plus 2 is 3, plus 3 gives us 6. So we would have an s value of 6 for the first 3 natural numbers, right? What if n is 4? What's the sum of the first 4 natural numbers? 1 plus 2 is 3, plus 3 is 6, plus 4 gives us 10. So this here would be 10, right? And then we would have 5. Let's stop at 5. So we'll have 1 plus 2 plus 3 plus 4 plus 5, right? The sum of the first 5 natural numbers, 3, 6, 10, 15. So we would have 15 over here, right? And you could keep going. And in part C, what we're going to have to do is we're going to have to find out for the first 50, what's that sum going to be. So notice that adding all of these up until 50, it's going to take quite a while. So what we want to do is we are told that this is a quadratic relation. And so what we're going to do is we're going to find the quadratic relation over here. Okay, now before actually finding it, what we have to do is we have to confirm that this is a quadratic relation. Now, how do we do that? How can we confirm from a table of values that this is a quadratic relation? Well, we could find the finite differences. And if the second differences are constant, then we know we're dealing with a quadratic. And we've gone through examples of finding finite differences from a table of values. How do we do that? Well, we would take the bottom minus the top. So 3 minus 1 would give us 2. 6 minus 3 would give us 3. 10 minus 6 would give us 4. And then 15 minus 10 would give us 5. So those are the first differences. Notice they're not constant, but if we take the second differences, so 3 minus 2, that would give us 1. 4 minus 3, that would give us 1. 5 minus 4, that would give us 1. So notice that these second differences are constant. And because we showed that the second differences are constant, and notice that the n values, there's an equal amount of space between all of them. I mentioned that in previous videos too. When you're taking these differences, you got to first make sure that these all have equal spaces between them, and notice that they're all going up by 1. All right, so taking these differences is fine. And then notice the second differences end up being constant. So that means that we're dealing with a quadratic, right? We did part A, we confirmed it's a quadratic relation by showing that the second differences in the table of values is constant. So that's it for part A. Now in part B, what we have to do is we have to find the actual quadratic relation. Now a quadratic relation in general is what? Y equals ax squared plus bx plus c. Right? But again, instead of using y, we're using s, and instead of using x, we're using n. So we can rewrite this as s equals an squared plus bn plus c. Again, it's not fully necessary for you to use n and s. You could still use x and y over here. It's just make sure that you label this as x and y and say what each of them means. So now what we got to do is we got to find this a, b, and c value from this table of values. And we've gone through questions like this before earlier in the course, where what we got to do is we got to plug in these values for n and s, and then we're going to have equations. And more specifically, we have 3 unknowns to solve for, so we need 3 equations. So we would use 3 points. So let's first start off with the first point, which is 1 and 1. So we plug in 1 for s, and then 1 for n, right? 1 to the power 2 is just 1 times a would give us a. B times 1 is just b plus c, and then we got 1 over here, right? So that's the first equation that we could use. Now let's move on to the second point. Let's actually write these points over here. So I'm going to plug in 3 for s, and then I'm going to plug in 2 for n. So we'd have 2 to the power 2 plus b times 2 plus c, right? And then 2 to the power 2 is 4 times a would give us 4a plus 2b plus c. So we got that right there. That's our second equation that we could work with. And then let's get a third equation because we have 3 unknowns. So we need 3 equations. We plug in 6 for s, and we plug in 3 for n. You could also use one of these points if you want for the third equation, or you could even use maybe like these last 3 points for all 3 equations. No matter which you use, you're still going to get the same a, b, and c values. It's just I feel like it's better to use the lower numbers so your numbers aren't getting too big over here. But if you use any of these points for the equations, you're still going to get the same answer. So plugging in 6 for s, we'll have 6 equals, give me a sec here, 3, right? We're plugging in 3 for n, so we'd have plus b times 3 plus c, so we'd end up with 9a plus 3b plus c, like that. Okay, so these are our 3 equations, and now we could find the 3 unknowns. So there's multiple ways to do this. Whichever way you go about it, you could do substitution, you could do elimination. Again, whichever way you go about it, just make sure you're going to get the same solution that I am in the end. So what I'm going to do to start is notice that these c values here are by themselves. So what I'll do is I'll isolate for this c over here. So if we do that, keep the c on the right side, bring the a and the b over, we'll have 1 minus a minus b. And then I'm going to take this expression and plug it in for this c and then that c. And then notice that we'll have two expressions only in terms of a and b, and then we could solve for a and b using those two expressions. So taking this here, I'm going to just do my best not to be too messy here. So taking this over here, plugging in for this c, right? We isolated for the c in the first equation. Now we're going to plug in this expression from the first equation into the second and the third. So we'd have 3 equals 4a plus 2b, and then plus c. So it's like we're adding this over here. So we can just rewrite it as is, plus 1 minus a minus b. Let's say this was like maybe 2c, then there would be like a 2 in front of that c, right? That we would plug in, and then we'd have to distribute that 2 in the bracket. But it's just a c by itself, right? So it's like plus 1c. And so we're just adding whatever it is as it is, right? Which is 1 minus a minus b in this case, like that. And then from here, what you want to do is you want to simplify the like terms. So I'm going to bring the 1 over. So we'll have 3 minus 1, which would give us 2. And then we'll have 4a minus a, which would give us 3a. So we dealt with these, we dealt with the 1. Then we have 2b minus b, which would give us 1b. Right? So we have a new equation here, and notice that this new equation, it's in terms of two variables now, the a and the b, right? We got rid of the c, which was our goal. And now we're going to do the exact same thing with this third equation. So we're going to plug in this for this c. So we'll have 6 equals 9a plus 3b plus 1 minus a minus b, right? Because we're just adding a c. Same thing as we were adding just a c over here. Bring the 1 over, we'll have 5. So that one got taken care of. 9a minus 1a would give us 8a. 3b minus b would give us 2b. Right? So this and this, all of these netted out to this over here. Right? So that's one way to go about it. You could have also did elimination. So you could have took maybe this and subtracted this, right? And then the c's would cancel out like that, and maybe took this and subtracted that, then the c's would cancel out. You could also take this and subtract that, c's would cancel out, right? Different ways to do this. You can try different ways even just for practice if you want. Just again, whichever a and b values you're getting, make sure you're getting the same ones that I'm about to get. So now what happens, we got 2 equations and 2 unknowns to solve for. And again, multiple ways to work with these two. What I'm going to do, the b is by itself over here. So I'm going to take the b and I'm going to isolate it. So I'm going to keep it on the right side. I'm going to bring the 3a over. So we'll have 2 minus 3a equals b. And then what I'm going to do is I'm going to take this expression for b and plug it into that b right there. So we would end up with 5 equals 8a plus 2 bracket this. Right? I took this expression for b from this equation and plugged it into that b in that equation. And now notice we have an equation with only one unknown, the a value. And so we could solve for it. So we'll have 5 equals 8a, distribute in the bracket, we'll have plus 4 minus 6a, right? Yes. So now we could bring this over. 5 minus 4 gives us 1. 8a minus 6a gives us 2a. Divide both sides by 2. To get the a by itself, we end up an a value of 1/2. So we have one of the values here in our quadratic relation. Well, now we got to get the b and the c. The b value, notice that we have b isolated here in terms of a, so we could just take this a value and plug it in here to get the b value. So b is 2 minus 3a, so that would be 2 minus 3 times 1 over 2, which would be like 2 minus 3 over 2. Notice that's like 2 minus 1.5, right? Which would give us 1/2 as well. But if you want to take the 2 over 1, show that it's 4 over 2 minus 3 over 2, get a common denominator, show a little more work with fractions, you can do that as well, right? So the b value is 1/2. So from these two equations, we got the a value, we got the b value. So what I'm going to do is I'm actually going to erase these because we don't need these anymore, right? All that's left to find is the c value, and none of these have the c value. But what I'm going to do is I'm going to still write out our solution. So we got an a value of 1 over 2, we got a b value of 1 over 2. And now what's left is to find the c value. Now the c value you can find from any of these equations over here, right? You could plug in an a value of 1/2, a b value of 1/2 for either of these, and then just isolate for c. I'm going to use this over here. Notice we already isolated for the c here. So we're told that c is equal to 1 minus a minus b. Well, we could just plug in those like that. What's 1 minus 1/2? That's 1/2 minus 1/2. That just gives us 0. So we get a c value of 0. So those are the three values in the quadratic relation. And so we are pretty much done part B. Now another thing I want to mention, if you plugged in 1/2, 1/2 for this a and this b isolated for c, or this a and this b isolated for c, you'd still get a c value of 0. So it doesn't matter which ones you plug it in. So what is the quadratic relation? What's the actual equation? Well, we just plug in our value. So we'd have s equals 1 over 2 n squared plus b is 1 over 2 times n plus 0, and the plus 0 we don't have to write. So this is the quadratic relation here. This is the sum of the first n natural numbers. And if you want, you could take this and you could test it out. So we use these 3 points, so let's maybe test it out with these 2 points. So what would happen if we plug in 4 for n equals 1 over 2, 4 to the power 2 plus 1/2 times 4. So we'd have 1/2 times 4 to the power 2. We got to do the exponent first, which is 16. 1/2 times 4 gives us 2. 16 times 1/2 is 8 plus 2. It would give us 10. Right? So notice that we do get an s value 10 as expected. What about if we test 5? Right? So if we do the same thing, but we plug in 5 for n, let's see if we do indeed get 15. So we would do 1/2. Now we got to do the exponent first. That would be 25. What's 1/2 times 5? That would give us 2.5, right? Half of 5. Let's keep this in decimals. 1/2 times 25, 12.5 plus 2.5 does indeed give us 15. Not 50, 15. I was thinking about the sum of the first 50 and natural numbers. I was kind of getting ahead of myself, right? What we're going to have to do in part C. Right? So as expected, we do get 15. And you could also test these as well. You could plug in 1 for n, or 2 for n, or 3 for n, and you will get these respective s values. Right? So that's the quadratic relation. So kind of cool how that works out. Another thing I want to mention before doing part C, you could see this in a different format. The actual most popular way that the sum of the first n natural numbers is shown is, we haven't really covered factoring yet, but what you could do is you could take out a half and you could take out an n. So the way this would look, we could take out a half and an n, and we'd be left with n plus 1. Right? Notice if we take 1/2 n and distribute it in the bracket, what's 1/2 n times n? 1/2 n squared. What's 1/2 n times 1? It's 1/2 n. So this is another way to show it. And then even putting this in a different format, we could take all of this, which is like over 1, and put it all over 2. So we could do n times n plus 1 over 2. Okay, so different formats that the solution can be shown as in the back of the book. This is a very popular format over here, right? But this and this, they're actually the exact same thing. Okay, so don't get confused if you see this in the back of the book and you got this and this are the same thing. Okay, and you can even test this out. You could, again, take these values, plug them in here. You do the multiplication up top. Well, first you would do the bracket, right? So for example, if we plugged in 3, 3 plus 1 gives us 4, times 3 gives us 12, divided by 2 gives us 6. Right? If we plugged in 3 over here, we'd also get 6. So either of these formats, they're the exact same thing. And so now what we can do is we can find the sum of the first 50 n natural numbers very easily instead of doing it manually, right? Adding all those up, which would take forever. We could just plug in 50 for the n value. So I'm going to use the original over here. So we'd have s equals 1 over 2, 50 to the power 2 plus 1/2 times 50. We'll have 1/2. What's 50 times 50? That would give us 2,500. What's 1/2 times 50? That would give us 25. So 1/2 times 2,500 or 2,500 would give us 1,250 plus 25. So we'd end up with 1,275. 1,275. So if we took 1 plus 2 plus 3 plus 4, etc., following this pattern all the way to plus 50, added up all those numbers, we'd get 1,275. So you can use these formulas here to find the sum of the first n natural numbers, whichever n you want.